Can you see my screen now? Can start. And do everyone hear me? Okay. Thank you much. Hope this goes well. Yes, of course. Just a second. Everyone hear me? I hope. And this for getting some problems before we start this. We have 1 hour, and I think that's sufficient for looking at the topic that I would like to share with you. Well, I'd like to thank the International Society of Food Engineering to enable this webinar. It's my pleasure to talk to you, and I'd like to thank the audience for coming along, whatever time zone you may be in. I understand that it's morning in America, and it's in the afternoon here in Ireland, and then it's nighttime in Asia, and so on. On the topic that has been kind of important for the industry and personally for myself a long time, on characterization of food solids for processing and storage stability. I have here a number of things that I like to talk about, and this thing I will talk about will have much to do with phase transitions and that type of things that you may have seen in my published literature. I start quite far away from what is the present today. I do a little bit of background and some scientific background, which is related to the history of characterization of food solids in terms of what they are in behavior, chemical behavior. I will talk about transition in freezing and dehydration, the common examples. Then I will have a number of comments on the properties of class transition. I will also talk about structural relaxation times, which referring to the non-equilibrium state of foods. Foods as characteristics and structure, concerns and for the future. And there's someone.
Para levantar mano y hablar.
Microphone open. I hear some extra in the background.
Eduardo, y su micrófono. Envío activado.
Someone talking to me. So, if we look at food processing and preservation, first it's quite important to look at where does it come from? And of course, there's always a need of making food stable for much longer periods of time than would be allowed by the nature and the properties of the food itself. We know that food has full of nutrients that are microorganisms, and we have to fight against those. One factor is water in foods. So we can do some tricks with water. We can take it out from the food. We can add salts to change the water activity, we would say. Sugar is the same. And we can modify the pH, and we can freeze the food. And also note that the food solids are carbohydrates, lipids, and proteins, and those are substances that are the nutrients. Look at the history of food preservation. Well, keep the water is one option, and there we need quite extensive thermal processing or other alternative processing methods. there has been a lot of work in that area, which we'll be about today because that's more on the microbial side. Defined water phase, we don't talk too much about as well, but that is the long story of looking at organic acids or fermentation methods which keep the food safe. What is concern is the water activity control, intermediate moisture foods that came quite strongly in the 1950s and thereafter. And there's a big milestone, the food stability map that was done at the end of the 60s. Also, another thing is the food polymer science was especially promoted by Harry Levin and Louis Slade in the 80s and thereafter. The background for the topic I'm talking about today, we could go as far away as to the early 19th century. The gentleman from William Prout, who actually often is commented as the father of food and sometimes father of nutrition. What I can give him a credit about is that he divided the food materials to the fractions, the solids of saccharin, which sugars, of course, oily, which is the lipids, and then the albuminous that time, which is the proteins. So that is from that era. So he had comments on the state of sugars. He referred quite strongly in his publications to glucose and the fact that it's a transparent fluid. Any materials and forms a transparent solid fluid, it would be quite stable in dry atmosphere, but when exposed to water, humid environments, it starts to get opaque and also to become crystalline. He had some comments also about what we call nowadays in molecular gastronomy, but that would be another thing. We moved towards a few decades thereafter. We could find techniques like spray drying and drum drying coming quite strongly into the literature on patents, and also early, about more than 100 years ago, industrial milk drying started, and that meant that there was observed quite soon in the behavior of the particles, especially with the water content and the relative humidity of the storage of powders obtained by drying. And some fundamental papers were published on the humidity dependence on those phenomena. Also, it was realized the lactose was easily crystallized in the systems, and there was alpha and beta lactose found in the many products. On the same time, soon after the X-rays were referred, there were used in X-ray diffraction techniques, and already in 1896, Weichmann published papers that were referring to crystallization of amorphous sucrose. The publication from World Congress on Applied Chemistry in Vienna, 1898. And what was found was that there was that could be monitored by the X-ray diffraction techniques, and all that it was a common phenomenon when sugar type of clear and candy were studied at the environments. But long after that, a number of publications appeared in the literature by a group of in California, and he published first papers on studies on class, which actually look at glycerol, propylene, and that sort of organic class formers. Also, in another paper with glucose, and it was really shown that these materials were quite good class formers. They also showed the typical behavior of non-crystalline materials in terms of the capacity of the transition, also the thermal expansion coefficient, and the mechanical properties, which are referred to viscosity, also dielectric properties, which could be monitored for these class formers of their class transition. So these were fundamental studies starting the understanding of non-crystalline classes. There was also a fundamental paper by McOver and Dye, published in Journal of Agriculture and Food Chemistry in 1956. And that paper reported findings of sucrose when it was dry and then exposed to relative humidity, as soon as almost years, which showed that there was a strong dependence on the relative humidity, how it carried itself. And what would be found was that if we look at here, there's the relatively low humidities, but high for sucrose, a rapid loss of the water that was taken happened. And one could also see that in the crystallinity of the material in the related publication by using X-ray diffractometer. So that was showing what happens in storage of these materials. At the same time, there was also a lot of work going on oxidation and relations in foods and chemical reactions. So is one of the people who were looking at the initial water absorption studies. He looked at the monolayer and claimed that it acted well with a boundary for free water. I comment that in a while. And also that the stability of beta-carotene, which is an oxidizing carotenoid, was quite stable below the monomer. So there were differences in stability depending on water activity. As said, the bound was free water, and I think one should realize that there's not really any good definition for the bound or free water. One should never say available water, because all water is available, but the capability of something to use water in different environments. And if we look at this old diagram, we could see that actually, if you go to very high humidities, where water activity is, there's plenty of available water, but the microorganisms don't like it. You buy a bottle of water, but there's still water with no nutrients. Hardly get anyone to grow there. So that is fully available. So the availability of water is not really controlling the growth of microorganisms. And we can also see the same in some of the molds growing in different Then I mentioned earlier the stability map, and I think there's a number of things that one could learn. Is the fact that water is available for browning at low water activities. It happens at low water activities, so it's not the reason for not happening or reducing the rate. The stability map was actually developed, and it was so that a number of reasons were dependent strongly on the water activity, and also sometimes quite well correlating on the molecular water content, the rest layer of water molecules that can be absorbed by surfaces. The that case is quite valid still in context looking at how does water affect stability of foods and then looking at the limitations for storage. Saying that it's not alone always enough. We have to look at also the fundamental studies that were summarized very nicely by an article of White and Cakebread in 1962. They were showing that the physics of food solids is quite an important factor in characterizing the stability and properties of boiled sweets, milk powder, ice cream, freeze-dried foods, because those are sensitive to water, but not only the water changes the properties, but they change in the state of components, especially carbohydrates. And find in the publication the high viscosity value that is often referred to be 10 to 12 Pascal seconds in a solid structure, while a rapid decrease of that viscosity appears when a material is allowed to pass transition because of an increase or increased water content. So that is besides the collapse, crystallization, stickiness, caking, and other props that happen above that. They also referred to the part that we saw before, but also Kausmann, who was professor of chemistry in Princeton University, and they have fundamental papers on collapse transition, and you might look at those if you have an interest. Before I jump to the next topic, I would like to mention Berlin had a number of studies on the water absorption of materials with non-crystalline lactose, and also that there were fundamental changes. If we look at some of these photographs that we have taken for storing spray-dried lactose at 76% humidity, we see that there's a big change. That is just spray-dried particles sphere non-crystalline states and allowed to crystallize. We see the tamaka lactose monohydrate crystals. Freeze-dried material is cakes that break easily, and you can see how they form needles in the crystallization because of the physical arrangement of the material. Professor Jorge Riffi from Argentina has published a number of papers on the absorption studies, which you may look at. So let's look now a little bit more in detail the class transition and how it affects freezing and dehydration. But what tools we need? I would think that one fundamental property that needs to understand in this is freezing and dehydration is a state diagram. You have state diagrams in literature, and I hear some state diagrams. I was excited, even when I was a student, by the work of Don Rasmussen, who you hear in this picture. This is not our picture. He published, when he was an undergraduate student, a number of papers with Professor Lewitt in Wisconsin on the favor of freeze-concentrated solutions of carbohydrates and cholesterol. What showed was a diagram that is very similar to present state diagrams. They observed melting of ice being dependent on the glucose concentration shown here, but also that there was a class transition that's typical for the dry material, but then a number of different transitions in the frozen state. So a person for this, and he's still active in Clemson University. Franks from Britain, he did another approach, very similar, 1970s, which named the diagram the state diagram for the first time. It was a kind of a supplementary diagram, and Harry Levin and Louis Slade complemented this with information on class transition and some on how the rotation temperature goes, how the solubility goes, and how the liquid state goes. What is important there is to understand the behavior of the solids in themselves, behavior with some water, behavior when water freezes out. And when water freezes out, one sees vitrification of the freeze-concentrated iron phase. So take the ice crystals away and look at inside the solids with some unfrozen water. Then you can find what happens to that at low temperatures. It forms a glass, it vitrifies, and the question is, when does it happen? That work is fundamental also in understanding freeze drying. Professor Judson King from Berkeley, California, he's still sort of active there, but he's professor of chemical engineering, and a classical paper by Pelose and King in 1973 explains how the freeze-concentrated material is formed in freezing first, so that you say that there's the ice and then the freeze-concentrated phase. When you have ice drying by freeze drying, if the conditions are proper, the ice sublimates out and the concentrated solid stays and keeps structure. But that is allowed to flow. What will happen is that these walls will go down and collapse and the capillaries, and there's no chance for the ice to sublimate, and it increases internally pressure, phase the drying. We call it collapsing phase drying. They did a lot of work to understand the viscosity, how it goes with the temperature, and then they identified the critical zone, how actually these walls need to be to have the collapse. And that works well. And they also had very similar to state diagram, where they could establish based on the measurement. Upon that, 1980s, the same group came with some fundamental ideas of in spray drying, and it's also a paper by Sandra Williams showing that a fructose-sucrose mix was behaving in terms of viscosity above class transition like many polymers, and we could apply the WLF Williams-London Ferry relationship to understand that. So we could then explain the freeze drying based on Pelose and King data. There was a lot of done on collapse at the same time by Tom Flink in MIT and Professor Marcus Carrel. Then the GAP-SOPs and isotherm models came about because they are important also to quantify the water contents and water activity relationships. And Cornelius van den Berg, he established stable starts and explained his water ballasticization. These were all behind the Williams work by Harry Slade. We have actually analyzed quite a lot of these data from viscosity measurements, etc., which are extremely time-consuming. What we have been able to explain is that if you look at the relaxation time above the class transition, you would find that the viscosity of relaxation time have a critical value for contact in spray drying, where needs to be allowed for particles to before they adhere to surfaces. And also we could say that the glass transition line is here, the black one, and the relaxation time goes from 100 seconds towards lower values rapidly above the glass transition. And there we could find sort of critical zone about the class transition where things start to happen in real time very rapidly. Also relates to the cryostabilization concept that was presented by Harry Levin and Louis Leiden in the 1980s with a state diagram and a lot of material showing how the different sugars, carbohydrates, organic solutes behave with water at low temperatures. And what was the T sub C prime, which did not really agree with what we call nowadays the T sub C prime, because that was more on the melting side, but there was a relationship established with that parameter and the kinetics above the transition, showing that physical-chemical changes like crystallization, reaction kinetics are in the related to the class transition. So they published a number of publications, but the idea is shown here that if you are above the class transition state, you have Arrhenius, above the class transition WLF, and far away from the class transition, you Arrhenius temperature dependence of phenomena. So what you would say that around the class transition, you have very rapid change in radioactive changes, or also properties of materials in this. The properties of the class transition itself, I think we'll look at those fundamental things before we can understand all that what I was saying before. And that is now pretty explained here. May have done measures with DSC. And often it can be a little bit problematic to explain what's the nature of the curves that are obtained, and they can vary quite a lot depending on the material, the different broadness, or they may have different indication of class transition, or sometimes they may have exotherms or endotherms. But that goes to the temperature dependence of the itself. It goes to its non-equilibrium nature, because you never ever can do one single class exactly the same again. That is with the molecules freeze and find positions that are dependent on the cooling or heating rate. And we could say that if we could heat a material with a rate A or rate B, we would have a different volume. If we had to be very low, certainly have a lot of volume disappearing from the material. If it's very rapid, we have extra free volume. And that is also relating to the enthalpy content of a material. If we have and heating at the same rate, we probably have quite nice class transition, same heat capacity over temperature range that we call class transition. That's then a material that we cool slowly and then heat rapidly. We will see that there is now an M. And that's because we, in slow cooling, allow the material to go to a fairly compact form. And the material is in the gaseous state. The molecules are frozen. They cannot move anywhere. But when we come to the class transition area, we're in plasticization, and there's a thermal water plasticization, molecules away from each other, and it becomes more flexible. At the same time, they reorganize, and that releases the heat. So, it requires the heat, depending on the state. So they can expand to get to the sort of more equilibrium state of the molecules. What they would have, they need more energy for that. If we have cooling and low heating, we would see this one and exotherm, because we this, and then the molecules can release the extra energy. And we describe all those phenomena by looking at rapid or slow cooling, and we can get different classes state. what I'm interested in, how fast these relaxations happen about the class transition onset. Of the onset is sort of a measure of a tensor value where we start to see real-time changes. And we can explain what we on the difference of scanning calorimeter, or more importantly, what happens about the transition in dynamic mechanical analysis or dielectric measurements. So we see that the frequency-dependent response to rest biomaterial. So we see that there is the higher curve, the higher is the frequency if we model storage modulus. So that's softening of the material about the class transition. So different frequencies we find different values. So if we look at the loss modulus, this means that when is the material able to have external heat generation, so slow frequencies are closer to the class transition than high frequencies. So we can identify where is this loss modulus peak, and we use that as a temperature value. We can find it what it is, and we could also say that our relaxation time is related to the frequency, and we could see how does the relaxation time and temperature above the class transition match to each other. Comment on the nomenclature and the use. And some people call enthalpy recovery as a relaxation, but it's not really an enthalpy relaxation. Enthalpy is not a relaxing function, it is a thermodynamic property, and we will see that it is related to the change on the molecular arrangement. So we can say it's a recovery or release. Then structural relaxation, they have the molecular rearrangement, so that we are measuring how fast those happen, and we have the relaxation time parameter to look at that. And that's what we can measure, the mechanical spectroscopy or dielectric spectroscopy or dynamic methods that I showed before. And oxidation, in fact, is the phenomenon that happens. Transition is the cause of the phenomenon, and the class transition is the thermodynamic kind of that we can follow using the expansion coefficient or the heat and that type of chemical parameters. So relaxations don't really measure the class transition. We have to keep in mind, if you do measurements on properties about the class transition, you probably are measuring something related to the relaxation times rather than the class transition itself. Sometimes there are misconceptions on that. And we need to do annealing thermal treatments to find what is happening. So, with the class transition of foods is happening of a broad spectrum of temperatures. Some generalities is that we find the class transition for sugars. They are nice class formers, relative to follow. We can see the water plasticization easily. And what we say also is that if we do this type of approach, the transition temperature of the dry substances against the logarithmic molecular mass, we have a nice linear relationship. Just with the protein transitions, T sub C prime is the class transition onset of a molecule concentrated solid phase. And the Tm prime is the temperature where in type of maximally concentrated system, the first ice crystals start to dissolve. So it's an onset of ice melting. They show the typical water plasticization behavior for materials and molecular weights. There are measurements for proteins, starch, which are more problematic than simple carbohydrate. The retardation has been followed. This is an example for those showing that it is happening when you keep the material, we call it aging, just below the class transition, 20 degrees below 60, 75, very low. So you can see that 24 hours, the return of entropy is quite much. Sorry, it is not below. This is the class transition is about 100, so this is very close to class transition. This is far away from class transition. This means that it's very hard. It doesn't happen much in 24 hours. But close to class transition, you see quite a lot of changes. I have here something about water activity and the food stability map. Some studies I did a long time ago relating to water activity and the class transition with for complex solids as the sucrose in strawberry solids. So linear relationship, but that relationship is practically quite useful because you can always have a slope and you can predict what if I have a water activity of 0.2, where is the class transition? We know that this would not be stable. And freeze-dried strawberries actually, and if you ever seen them, they will be quite fragile and nice when they are low water content, they are crispy. And if you look at the temperature here, room temperature, it's almost 0 water content. They're nice, but if you expose them to a little bit high humidity, not much than 0.1 or 0.2, they really get wet and soggy, not nice any longer, not crispy, and there are quality changes. So I can say that there's something critical happening, and what we have done then to add class transition to the stability map, and we can then identify a critical water activity named as that where the temperature and class transition meet, and that would be quite low for these strawberry solids, but it varies with the molecular weight as shown in previous diagrams. But that would also explain that there's stickiness, collapse, loss of crispness, other happening soon after that, exceeding that critical water activity if the temperature were constant. So the diffusion limited reactions also go up, and there's a number of studies on that. Sedation is very different because you are looking at a phase of the often happens in the glass formers. It happens in compounds that are dispersed within that. The diffusion of oxygen in the glass may happen, but often it's a barrier. If critical water activity and the reactant mobility, we say that the class transition actually is a property that is directed to class former mobility. Then if you look at the diffusion and reaction rates, we have indirect effect. The complex, we have to, in the microstructure or even nanostructure of the food, think where are the class formers, what are the reactants and how they move, and how they may be locally located in the system. Just like looking at different particles within different solids. So all solids are segregated. There are multiple phases in foods, multiple states, and we have to be aware of those. So we move to water and class transition with some comments on those. We did a lot of work on the freeze concentration, and we related to T-sub-C and T-sub-C prime on kinetics with Professor Markus Karel in the early 1990s or late 1980s. And we did quite substantial work on the class transition of sucrose to show how did actually the class transition happen, followed by melting of ice in freeze concentrated systems. And that, if you have a little time, you could look at this paper and see how the melting is actually corresponding to the T-sub-C prime population by Harry Levin, Louis Freud. The prime here is the onset of the class transition. The problem is that these two transitions are overlapping, and you may not be able to identify where exactly is T and prime, but neither can you see the whole class transition. There, that the class transition starts, has its onset, and is immediately followed by the T and prime, so it doesn't have an. There is something we don't have time to test. We also have a number of measurements to show that the temperature or the ice formation is very time dependent. Whether fructose or glucose or sucrose, and solution where there's some water that can freeze, but not too much. We can see that the longer we allow freezing to happen, the higher the class transition, and then we can approach a maximally freeze concentrated state. We can do that and show that what we were looking at as T and prime and T sub C prime were actually validated. Also, then, if we look at the class transition temperature of water, we have publications that show that at around minus 135 Celsius. And these data show that that's where it tends to go if we have the capacity measured and published for unfrozen water. So the area of water class transition is very complex, and there's a lot of published on that. This diagram is quite fundamental to understand. We have here the one was published with Professor Carrel, but I would like you to pay some attention to this driving force system, which is showing typical transitions in materials. Temperature, cone or liquid, we see melting, we see class transition. You need to care too much about what's the material, but think, for example, that this is a sucrose. You would have sucrose melting at around 190 Celsius. Rapidly cool the sucrose, make a candy, and you cool it to 50 degrees without water to get it into the solid state. Now you do that, you only cool the material, but you probably can cool without crystallization. So it forms a glass, vitrifies. If we what happens in terms of thermodynamic properties is that there is the Gibbs energy that is if it's stable or not. If the Gibbs energy is lowest possible, for the crystals it would be the low value. We have a non-crystalline matter. We extend the liquid area by the liquid without crystallization. And we find that for the solid, it becomes somewhat different. We have there a change in terms of Gibbs energy in the non-crystalline material. Often, in this state, the property is to keep material frozen. Models cannot move. They cannot go back to the equilibrium state. They are frozen. If we go to above the onset of class transition, we have a big driving force, and the materials want to change back to this equilibrium state. And the more away they go from that position, the smaller is the difference, but there is a difference. So we say this is a critical state for a number of things in the foods. Our studies have quite strongly looked at, and I find some of the tools for the diagrams which are important here. There's a lactose state diagram where one would to know the behavior of lactose in terms of water content and temperature. So we have to opsonize the term, we have glass transition, and then have some crystallization data. We could then translate this to the diagram by converting the values to water content and to glass transition, and we could explain many things in real life. On the other hand, the state diagram could be looked as a map showing relaxation time. We have a class transition, so it's a solid. There's really much happening, but it would be then more softening, and we see that there is quite a rapidly happening things. Same as the relaxation time goes down. So the time needed for a material to relax change. To look at some of the water properties in non confined environments, which actually become more important to understand some more complex food systems like proteins. How water in them? I comment that soon. In the industrial summarizes some of those. Why would you have any interest in this type of characterization of food solids? Because we can do extrusion, we can do spray drying, we can bake pizza, so we can have cheese snacks, extruded snacks, we can have Pop-Tarts, we can have licorice or ice cream. I will name it. There's a lot of things, even bread and other materials. So where are the temperature state with some water content, and what are the structure forming annotations by the solids themselves? So one could quite a lot of interest in the industry on that. For those and better characterization, we need some understanding of the structural relaxation times. Our approach being fairly simple. It's a Triton system to measure dynamic mechanical properties. It's measuring tumors. It's easy to cut materials and freeze them with lamps, but we have to use pocket. These are metal sheets that are fixed to the system to measure it in ping or often ending, and how the powder is behaving in the measure. We can see typical loss modulus curve or tongue delta curves, and we can also use electric measurements. This is a parallel plan between the plates. You can place a sample that becomes conducting material, and we can get similar type data as one gets from DMA, but on the dielectric properties. But we have an interest. You may see some papers by Professor Austin, and he has made this fancy diagram with a lot of material saying that if we have silica class, it's very Arrhenius. Plot the C over T, and it's a straight line. While if you look at some other materials, they are very curved. So you could measure the curves here and say that they have a different D value. And that comes from the Tamman Dixon, which I so soon, but also here is a material that is relationship converted from the WLF equation, showing that Tamman filter and are actually comparable. But if the equation is more Arrhenius type relationship, following this type of relationship, we could get here trehalose, glucose, glycerol, water, they have different fragilities. But about a material that would have the same TSP, these have different TSP. And if we look at this equation, we say that obviously they have the same point at T divided TSP divided by T, because it's always one. But if we have different class transition TSP values, they are in a different position in the scale, would automatically have a different fragility. So it doesn't really make much sense to me to look at this. So here are the two relationships, and I have here VTF, which uses B, and the fragility parameter D. If you write that the times T zero. And if you left, we plot data accordingly. We could have silica class here, and then we could have WLF data for a number of materials. They are here, glucose, water. They go quite clear. But we have a zone that is a critical zone below the class transition for a number of food solids. Then you look at the WLF relationship. This relationship, to T minus T sub C if you put G here instead of S. And the C1 here is a measure of how many decades is there a drop in the class transition when you change to T minus T sub C. It tells you where is that going to have an infinite value. The red curve here is what is the original WLF, showing that here's the point where T minus T sub C 0, so the class transition. 100 seconds would be the value. At C2, we could go 51.6 degrees low, and that's where the crescent infinity. And then we look at, does it mean? It would mean that the classic gets stiffer and stiffer and stiffer and stiffer forever. I don't believe that. That if you look at this is here, the 17.44 below 2. And that means it can't really get any softer. And then if you look at this green line, the difference is that now the C1, that's positive, and we say that this actually goes nicer because then you have some top parts of the class, and then it softens this above transition. In fact, some of the dynamic mechanical analysis data, we have done it for mixture of trihalols and WPI, we see that actually it softens nicely above that. But water concentration, we have different T minus T sub C. Now we have taken an allowable now decays from 100 seconds to minus 0.01 seconds, which is the point where stickiness in spray drying or other relevant flow. I can show that if we take that as a strength parameter, then we could say that depending on the composition, we can measure what's the strength. I can apply that with materials that we know and use it when we want to determine this in spray drying or freeze drying, collapse, and so on. So we know how much we can exceed the class transition. If we add water to the material, we would see that there's also some changes in these parameters, and the more water have we above a critical value, we get very rapid changes. The food composites, we don't have too much time, but I would like to mention a few. Freezing, we certainly do and that if we out the water, we could have limits of how the material was frozen, and we have sugar glass surrounding some dispersed fees, and we could say that we have fairly good microencapsulation and protection of these components because they are surrounded by solid glass, and there's work done on that in early times. On the other hand, if we look at some of our data, we could say that it is making quite a big difference what sort of solids are in the material that we put in a freezer. This is an example of different DE values of maltodextrins. We can see that DE20 makes a very different structure from DE4. They are frozen at minus 20 or minus 40 or minus 80. So the freezing rate has an impact on the size of the crystal, but so does the DE, which relates to the melting point depression. Based on that, we could actually make an analysis of the number of pores, which means how many nuclei, how the nucleation happens, and also how the wall thickness is, which is important for protection of sensitive components inside the freeze-dried matrices. We'd also make an analysis that is not quite well shown, that you can different freezing point depressions of different solutes, and depending on the class transition, you can also freeze them differently at different temperatures. Or if you change the size solute, you again would have quite different behavior of the materials. Drying, there's quite a lot to understand in structural formation because solids characterization. This is a schematic of a concentrate going to the dryer and then cooling a little bit because of evaporation, forming a crust that then be dried on the surface and then cooling that to below transition to allow particle flow. You have particles that flow if they are not solid. If they are somewhat liquid on the surface, liquids go together and then form one single part. So if we look at one component systems, we have lactose freeze drying or spray drying, and we have the crystallinities varying depending how they have been dried. In spray drying, we tend to get more crystallinity than in freeze drying. The composite with I mean is that lactose is here alone is spheres, but if we have some proteins mixed with the lactose, we have different appearance of the particles. They are dense and they have skins that is often absent from sugars. Then if we look at systems with lactose and proteins, we will see that they form a carbohydrate phase. If you look here, the carbohydrate is that is between the protein. That's more on the green, and the carbohydrate is the yellow material here. If we look at then the protein is dispersed nicely. If we have we would very different structure if we have made process or microfluidized system. So this is much more uniform that has been microfluidized, and we see small fat particles of all that we had put into the system. But we again can see that the class former is there, a continuous phase that entraps very nicely the oil particles. This is a cryo-SEM picture of this material. The protein and distribution of materials gives also look at how did the materials actually have differences in their behavior. And if we look at the properties of composite systems in water absorption studies or class transition studies, we could make the here is studied by some time ago. Dr. Noise Podes was measuring lactose with MD9 maltodextrin, and you can see that it's actually following lactose. The maltodextrin alone is far away, and tells that they mixed well together, but their classification is not much different. They actually do crystallize very differently because the small maltodextrin molecules, if we have those there, they are extremely good disturbance for the crystallization. That what I wanted to emphasize is fractional water absorption. On the other hand, we have to look at the composition of a food, and also where does the water go. And the earlier pictures show that the fat is in a different phase. It doesn't care about water. But also lactose and protein components, or sugar components, protein components, they take up water differently. If we look at where does the water go, we could show that we can add the different components or protein capacities together, and we can get counting lots of fractional water content, fraction of different water associated with the components provide the sum, and that is what experimentally identified as the water substance or the system. It have a substance that crystallized not as well as lactose could measure how much lactose was in the mixes, and we could get a full sorption isotherm for lactose that was never published before. And can be used to quantify how much water at different crystallization conditions is released by the lactose systems or some other sugar systems. Also, what we want to show is that if we look at the crystalline behavior, we have some old data from myself that we published with Professor Carroll on time to crystallization about the class transition. They are very parallel to each other. So that means that they have a difference in relaxation time. This is measured by DMA, and this is practically the Debora number that is describing the relationship is very well established for this type of relaxation time versus time to crystallization. And then that indicates the importance of understanding relaxations above the class transition. Proteins are very different. We have some initial work on their transitions, and this is showing a rapid picture of protein components. Transition may be found at low temperatures, but comment on that. Then we have an end term that is not well described in literature, but there's some data on that, and then denaturation. If we look at albumin, it's this dehydration transition, and then also reversible the protein, and then aggregation at high temperatures. Beta-lactoglobulin is somewhat different because its hydration happens, but it's slower, so it's not visible in scan. The low temperature protein transition actually could find transition or actually alpha relaxation for hydrogen water on the surface of the protein. So that is something confusing many studies because you may claim that there's a class transition of protein, but it's not. It's a class transition of water that is separated from the protein, and we had the establishment of that. But that allowed us, with the fraction of water sorption for the first time, to complete diagram for a mix of protein and sugar. And we put the sorption isotherms of those together with the transition curve of a mix and hydration water. We could quantify how much water was in the protein in the maximum freeze concentration and how much was in the carbohydrate fraction. And we say that protein with this water content have that and that much water to freeze out from the protein, with how much it dehydrates in freezing. And we could say when does the water get the glass, etc. The fundamental axis to conservation studies that should take that on board. Final words about dehydration characteristics. We have shown that the collapse temperature that I introduced earlier and the class transition temperature are strongly related. So very good correlation, and we could say that collapse time and relaxation time related, and there's a fairly good number explaining that. So we just to use the strength parameter I introduced to characterize how it happens. It applications in drying, and this type of approach taken to pasta drying industries, where you like to keep close to the class transition when the water is reduced towards this end, and then you can enhance the diffusion and keep the structure proper. But you also improve the quality in many other meals. And when you know the relaxation times above the class transition, you have much better ways to do that. And if you apply that to spray drying or air drying, you can make compost and formulations that are easier to handle. drying, we could also look at the volatile retention. There's work on that and so on. So that's quite important. Some is about emulsions for spray drying, because we have used to make a continuous matrix in the lutein and carotenoids that have a whey protein interface. They have a whey protein and a polysaccharide to have multiple layer interfaces, and we have looked at the stability in that type of systems. When you do the powder, you have to have the class former to do the structure that affects the first oil and brings to the solid stable state. And if we expose these to different humidities, you could study the properties affected by the class transition, the structural changes, and so on. So we have investigated layer emulsions and the beta-carotene loss above and below the class transition and the stability. But it's somewhat complex in the carbohydrate analysis, because you have ionization and you want to get the different isomers. We have concentrated of all-trans beta-carotene and lutein concentrations in spray-dried and freeze-dried materials. So we have followed them in experiments, we can see that there is two steps. First, especially in spray materials, the loss of rapid loss, because there's always some air occluded in the material, the air in the particles that's consumed, and that causes a rapid loss, and then less rapid loss, so two different kinetic phenomena. SL emulsions, so one single layer of whey protein, is typically less stable than the layer emulsion. So not only the class properties are defining the stability in processing and storage, but also the way one defines the interfaces has to play a role. We think that is somewhat hydrophilic and then complete lipophilic beta-carotene. We look at their behavior. We have a little bit different kinetics for those. Sometimes has a higher digital dependence, especially about the transition, because we believe that it is located on the surface of this is a particle. This is a Raman image of a particle that has no internal structure with some that are air, and then there's dispersed particles with the carotene. But if we look at these, lutein is mainly on the protein surfaces. We can easily see that. But beta-carotene is not that visible because it's immersed in the oil, and we cannot see that in the SCM. So we will then claim that the lutein system is a sort of antioxidant. It is up the first radically coming to the system, and it changes, appears because of that. The question of the free volume role in oxidation of lipids that have been in different type of systems, what we can conclude here in these studies by Professor Dross in Germany, in Berlin, he has shown that there is more hydroperoxides coming from matters with big weight and smaller molecular weight. And what we can conclude is that the smaller sugars actually make classes that have smaller free volumes. And this confirms on our studies what we said about lutein, that it goes to the surface. So actually the oxidants on the cell that acts there and stops the radicals or other diffusing components from growing oil, and that has been shown in the studies as well. almost in time, and sorry about the rapid comments on the final things, but I hope you got some ideas where applications are quite a lot in utilizing this information. So the relaxation times are really important in taking characterization data of solids into the real picture and into applications, and that's when that we will get effects. Strength parameter, what we developed, I think that's a good and useful tool in many applications to show how much can you exceed if you change the formulation. And the formulation then is a tool in hydration and freezing and extrusion and many other processes where water relatives are looked at to compositions and formulations for applications. So we can find many novel solutions, and I think in the freezing area especially there is quite a lot to do. For the future, I would say that relaxation times and crystallization, they are uncoupled actually in many in conflicts. So proper relationship and the use of strength parameter with knowing that this apparent C can with lower pull loss decrease in relaxation times to characterize solids, plasticization impact on strength parameter, multi-structures and innovative design of particles, that's important, and then it happens on nutrients and crystalline, non-crystalline composites. Something that food designers really have to look at, how to engineer that type of systems for assistance, the processes, to all the applications, and the impact on water. We can never really emphasize that. So, comments. I like to tell you that there's a very hopefully nice symposium food engineering coming on 17th May 2016. You can have some information if you go to Academy. It's organized by European Academy of Food Engineering at Samper Conference at MIT, and you can see the program in the website, or you can register at MIT conferences links. I suppose it's another thing that has long time to look at these type of things. As a symposium that was run in 1974, the first isotope zone here, there are many people who have contributed to the area I've been talking about today, many names that you may recognize, and some who still are very active, like Ted Raposa, and the other one that is coming that's in Switzerland, in the Olympic Museum, so it's a nice place if you are interested in sports and look at the water at the Lake River that is just in front of the Olympic Museum. So perhaps you can have an opportunity to see many of you there. Finally, I like all of you who have been listening to me today, and also all the people who have contributed to what I have shown today, and all the funding agencies which have provided money being there to enable our works. So thank you very much for your attention.
Well, thank you, Dr. Rus, for your presentation. We will now proceed with a questions session. First, I would like to show you how to raise your hand in case you have any questions. We will open your microphones one by one. So first, I will share my screen to show you how to. First, may you close your web screen for a while, please?
Yeah.
Stop sharing your screen, please.
Where was that command?
So right side, right where you of the WebEx meeting center, you have the participants menu. You can open. You should see your name in which you use to register or to enter the meeting room. You also have three icons right next to your name. The first one is right a hand, a camera, and the microphone. So the first one is the one you will need to click in order for us to open your microphone and you can ask Dr. Rus any questions you have. What's clear? You can. Okay. Well, I'm doing it once again, but now I will share my screen. Again, this icon over here is the one you should click on in order for you to ask any questions and us to answer, or maybe Dr. Rus. So I'll stop sharing the screen now and proceed with the first question.
Yeah.
Maybe Sai can open her microphone, please. You know, that's the question. Other questions? Saira doesn't have a microphone. She's writing the question on the chat. Any other one who has any questions about the presentation? Here's a question by Saira, Dr. Rus. She would like to know whether your research team is analyzing fatty acids or just a lipid fraction on the samples.
The acids as such. Can you hear me? Okay. Well, fatty acids in the systems, we haven't really looked at the fatty acids as such because the lipid phase hasn't been the main concern. If I understand the question correctly, you'd like to know how the fatty acids may change the lipid composition and so on, and how that does affect the stability of the carotenoids or other components. We haven't really looked at that. We've done some work on different oils. We have had hydrogenated palm kernel oil, which is very solid. On the other hand, we have had also very liquid rapeseed and sunflower oil. So the fatty acid composition is very different, and you certainly can see that if you have a solid phase, it's a different profile to solve oil-soluble components. But completely different story.
Okay, we would also like to know which is the yield you obtain from the lipid fraction.
Yield of what? Don't exactly understand what is the yield that she's referring to. Is that the yield of the carotenoids, or is it can you specify a little bit? In general,
we're still waiting to see what and from Zaira. In the meantime, do you have any more questions for the participants, maybe? You can also use the chat room, the upper right corner. Post any questions you have.
This is calling all the lipid fractions. I still don't understand the question because okay, the carotenoids, of course, you're looking at how much of those we obtain. Well, it's a fraction process in analysis. And we believe that we get them all, and we get the system of bases with carotenoids. We have a cocktail solvents to do that. But is the separation of the lipid fractions, and of course we have a systematic way of operating so that we have standardized analysis when we're looking at time-dependent loss at different conditions of the carotenoids. So I think in the lipid fractions we don't fractionate the lipids, but we extract the carotenoids. I hope
no, she hasn't responded, but we hope that would make it clear. So now from Luis Cabrera, he asked how can I distinguish a glass transition event from a denaturation event in complex matrix such as proteins?
Other events, that's what I was saying. Okay. This often difficulty. Now I have some concerns about the proteins overall, but what you usually should be able to do is you are looking at class transition. You are looking at the transition that is reversible. So you will analyze the material for the glass transition, heating at a given rate. If you find something that you will think is a glass transition, you should be able to find that this glass transition is, first of all, clearing, cooling, and heating. And every number of cycles you do, you should find it again, because it's reversible. Another thing is that if you have worsen in water content, you see that in most food materials, you will have a strong dependence of water content. Actually, you should be able to see how much the transition is moving with water content. If it doesn't, probably are not looking at the glass transition. Or if it doesn't appear again in recycling, then you also have a problem. But you have to be careful with water content and material. Products often have multiple transitions, and it's very difficult to identify which is a glass transition if there's a glass transition at all. Those are concerns. Also, the glass transition for protein can be very broad. The same is true with polysaccharides. But again, you should find a more narrow transition with increasing water content. We would that the proteins, if they have glass transitions, they have more frictions or certain chains areas where the glass transition, of course, differ, and it becomes very broad transition, very difficult to characterize.
Well, thank you, Dr. Roos. Are there any other questions from the audience? It seems as if we are done, so I would like to once again thank you, Dr. Roos, for your presentation.
I thank you and everyone else.
So this webinar session has been recorded and it will be available. We will be sending you the link. We look forward to see you on the next webinar session on the ISFE.
I have one question, if you don't mind, and that is, can you roughly tell how many people we have in the audience and how many countries are involved? Hello?
The staff supporting, so if he could please show the correct statistics.
Oye, una pregunta, es que me está preguntando el escritor cuántas personas se conectaron. Ajá. Ok. 40-45.
Around 40 to 45 people connected from the United States and America. Well, so if we don't have any other questions, any other comments, Dr. Roos, you want to share?
But that's wonderful. So, thank you very much for taking care of this excellent experience, and everything worked well. I think people could see it live, and there were audience, so that's good.
Well, we hope to make it even better for next month. And again, thank you. Have a nice day, everyone.
You too. Bye.
Bye.